the incline. Okay, so well, I say I'm recording. Yes, it's recording. All right. Cool. No, new page. New page. Pop up, and away we go. Okay. Wrong screen. Don't get carried away on me. Right screen. Okay. All right. On the world of stuff, we're going to do incline next. So, all right. And of course, it's a submerged surface. Let's get a nice little ruler up here. Do I have an angle on that? 1 to 2. 1 to 2 is what angle? 1 over 2 rise over 1 run is 0.5. That's, I don't know. Screw it. I'll just draw it, and you guys can have some fun sorting it out. And engineering artwork. It's always so much fun. Yeah, we're good. Okay. All right. So we'll play with concrete, but you can make an earthen dam out of this, other than it wouldn't have a vertical back. But our water is on this side. Okay. All right. Now, oops, get out of there. Go away. Our depth is going to be 30 meters.
Is that those little triangles inside the
just represents concrete. Okay. Actually, there should be some down here too. Yeah, remember, so concrete, and then if you see this one, earth, it's about all the ones I use. So, all right, so we got 30 meters down. Oh, I did this in metric. Shame on me. So we literally have this. We have a 1 and a 2 for a rise. So 1 for run, 2 for rise. Which means we need to find this theta up here. Okay? But we need to have some numbers here. So let's do this. Let's get rid of the ruler for a few minutes. So we're going to find the resultant. Okay. And center of pressure. You guys get the gist. When I write down COP, we're looking for center of pressure, right? Okay. And we're going to assume we have a specific weight equal to 9.81 kilonewtons per meters cubed. Okay. Dam is 100 meters wide, which is a big dam. Mm-hmm. Okay, so far so good. Mm-hmm. All right, step 1. find theta. Oh, that's not z. Sorry, that's 2. Come on. 2 over 1. And that turns out to be 63.4 degrees, which is kind of cool. I put that at about a 60-degree angle. Almost know what I'm doing. Almost. You get carried away. Everybody good on that? It's not the rocket science we're really worried about. Okay. Step 2 is start putting a free body diagram in this thing. So, and that's going to be the fun part. Ruler back. So, and I'm going to try to over exaggerate this. So give yourself a lot of room as you do this, because it's going to be messy. All right. So we are 63.4 degrees here to there. Okay. Cool. Get out of the way. So I want to do this here, and I'm going to switch colors on you just so I can keep things separate and straight for you. But we're looking at that surface there, okay, we got to deal with, and we're going to have a resultant that's perpendicular to the, so 64, 90 is 28, give or take. So that'll be our force resultant, okay?
That's not 90 degrees?
It is 90 degrees to that surface. You know, you really should sit someplace else other than the wings of this.
No, but I want to.
Yeah, you can sit back there. No. Leo's bored. He has no company. We already know from construction management, Leo runs a crooked company. He was the target of my examples today. Yeah. Why does the company keep 10%? Because Leo is crooked. Or why does the owner keep 10%? Okay, so everybody good so far on the free body diagram? We're not even close to finish yet, but okay. So our fun thing is, and I switched to red, I did. So think about this. This is our pressure distribution that goes up through here, and I probably should draw it like so. Okay, so as you think about this, and you definitely don't have to get into this much sketching when you do these problems, but you need to think in terms of the concept. Okay. But these are your pressures. Okay. And then somewhere in here, we will have a V, or force vertical. Okay. So I'm going to give you the length there first, but we're going to actually go calculate it. But it's the question of, so thinking back in your world of statics, if I know it's 30 meters down vertically, I guess I could put that back in this drawing. 30 meters down. Why is it 33.5? Yeah, we're looking at that triangle again. Okay. Which was what I was trying to get you to think about the day in lab. Which, by the way, I know Matt talked to you, and I asked him that afternoon when I saw him about their errors from last year.
Yeah.
So the only one that was in 5% was the partially submerged above, vertical. The rest were 30s. It's like, so that
Yeah, but our partially submerged
was 30.
is like 18 and 30.
Yeah. So I think it's just the experiment. So when you do your labs, just write up where you think the potential error is, because maybe someday we'll actually find time to actually go figure it out.
No, I mean,
It's weird though that last year they got partially submerged
Yeah, on the nose.
on the nose. I don't feel like we did it.
So, anyways, so just to figure out where L came from. This is a really obtuse triangle. It's not right. There we go. I like that one better. Okay. So I know this is 30. Okay. And that one is 64. Okay. So if I'm looking at finding L here, so it's the sine, because it's the opposite over the hypotenuse. So we got a sine of theta equals 30 meters over L. L equals the sine of 30, or sine of theta, times the 30 meters. Okay. No, I did that wrong. What the hell? It's been one of these days. 30 meters over sine of theta. Okay. Which gives us 30 meters over the sine of 63.4 degrees. Okay. Now, truthfully, you could just keep it in the 2/1, run over rise, or rise over run, sorry, and you'd get where you want to be. Okay, but we converted, so we're there. All right, and that gives us 33.5 meters. Everybody good with the trig?
Mm-hmm.
There's a reason we make you take that. All right, so that gives us our L. And our next step, anybody want to, where'd it go? Oh, this must be one of those problems I ran over the next page. Oh, goody. Where'd it go? Oh, yeah, there we go. Okay. This has got to get ugly in this format. So, small concept topics here first to start with. So, when I get the pressure due to specific weight as we drop in height, we know we're going to come up a third from the bottom, and that'll be the vertical pressure. Okay? But ideally, that's really pressure applied over here. But pressure has to be applied vertically or perpendicular to the surface it's on. Okay? So, it's time for a better free body diagram. Pick a point. Okay? And then let's lay out all the forces that are really playing here. Okay. So, first one. I have a W, big W, it's weight. Okay. I have a force R, or force V, I mean, or yeah, I wrote force R. I want force V vertical. Okay. And then between that, I'm going to have, and I'm going to put you in red. I'm going to have the resultant force FR. Okay. And I'm going to know that my center of pressure is this distance up here. Okay. And that will be labeled LO when I have a L equal to 33.4 meters. Okay. What's up with Microsoft OneNote? It keeps doing stupid stuff. Is it 0.4 or 0.5? What did I do? 0.5. Okay, sorry. I'm dreaming to myself because I didn't want to scroll back up. Yeah, 0.5. I can make numbers up just as the best of them. All right. So from this one here to here, where is this number? So this is 1/3 of Z, or 1/3 of 30 meters. Okay. So that COP is 10 if it was vertical. Okay. But we get to go play around with all the other numbers here. Actually, that's not an O. That's supposed to be an R. Nice of me. Location of the resultant. That's what I'm looking for. It'd be nice if I read the whole screen. And can I make you smaller? This is ridiculous. I can't see half my notes. It's going bigger. There we go. Okay. Oh, cool. I make reference to the textbook, which you don't have. For you, though, I'll write it in. All right. So we're actually going to play with equation 3.9 out of Gribben. Okay. So that you have it. If you do see a book, you can at least go find it. But here's the equation. So we need to figure out the force that's going to act on this thing. All right. So the force is equal to 1/2 specific weight times the width times the Z times L sine of theta. Ugly. Ugly, ugly, ugly. Okay. Oh, by the way, this is FV. Okay, sorry. I missed labeling the units, or not the units, but the one we're looking for. All right, so I really did it that way, did I? Okay, fine. Do it this way. change the style this year. 9.81 kilonewtons meters cubed. I took everything and divided it by 2 after I did the half. And it's like, that's not me usually. What the hell? Just had a bad day. We're 100 meters wide. Okay. And by the way, I want to point out here, width, not the big W we're going to need later here, okay? I know there's the W's in here, but you want to be careful to get the right W, because if you're going to make a mistake, I guarantee that's one of the potential places that you can screw up, okay? Now we have an L that's 33.5 meters times the sine of 63.4 degrees. Okay. And keeping the units the same, which you're going to love, 440,775 kilonewtons. Tell me water doesn't have a lot of force. Yeah. So we can make that a little easier if we want to change things. And we can do it a couple ways, but we can go 440.8 meganewtons. Okay. We could do 4.8 times 10 to the third kilonewtons. Keep going any way you want. We could do 0.44 times 10 to the 6 newtons. You got to keep this in perspective. I guess is what I'm after. So if you think about it in meganewtons, at least you got some fathomable nature that's nothing you've ever dealt with, and it's huge. If you do 0.4 times 10 to the 6 newtons, like, yeah, okay, it's a number. Okay. Question, Dr. Eagle?
I was just, I've seen it from several of you, the scientific notation where you've got like hundredth, not hundredth. Why is it not just always 4.4 times 10 to the 6? Where you've got a single digit.
Traditional traditional standards of engineering. Yeah.
I don't like it.
Don't have to. Just have to adapt to it. Raiden?
I have a question from earlier in the equation where you calculated F of B and it was like 1/3 C. And I get that, but how is that equivalent to COP? Because isn't that like
It's not COP, but it's COP is if it was vertical. So I'm trying to relate the vertical to the horizontal. So normally, all I'm looking for is just trying to get that as a perspective. So literally, if I know it's 1/3 off the bottom, this should be really out of whack. Okay. So I wouldn't do that normally, but I was just trying to get you to think about where it is in space. Okay. With me? Okay. Sorry, if that's confusing. This wasn't meant to be. All right, so we have V now. Let's go find the weight of the water. And I do mean this is big W. That's extreme. All right. So I have that. I have the volume of the water above it. But we're going to change that to this equation. Did I tell you the equation? Yes, I did. Cool. 1/2 L sine theta L cosine theta And I need a parenthesis there, and a parenthesis there, and a parenthesis there, and a parenthesis there, times the W, the width. Or we're going to clean this up. This is the one you can write in the, well, I used to say the cover of your textbook, so you don't have to go looking for it. You can put this on a cheat sheet someplace. Okay, and this is equation 3.10. Okay. Which one of the two would you rather deal with? But here's my point behind this. Okay, so this is, the weight of this is the specific weight times the volume of the water above that free body diagram point where the center of pressure is going to be. Okay. How much water is hanging up there? 100 meters wide, 1 feet up. Okay. It's easier though if you break it into this bit of math. And then when we settle down, let's get the L's out and we'll square them. And then all we got to deal with is sine of theta, cosine of theta. It makes life just a little bit easier. And a whole lot easier to remember. Okay, but basically, we're talking about the volume of water there. Now, the reason I want you to pay attention to that volume of water and W is water has weight at any given point in space in that body of water. Okay, but what happens if I give you a scenario, we got an inclined surface, but we have a flat surface that goes over, and then I got another step vertically up. So I literally have water sitting like this. Here, 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 I cap off, and I got water there. How much water actually sits above that center of pressure? So we're going to do some problems like this. But we have this volume of water up here. Then we got this volume. Sorry, let's do that right. We got this volume of water here to deal with. 100 meters wide. Don't forget that. Okay? That's a lot of weight. You ever pick up a 5-gallon pail? Now pick up 100 meters of 5-gallon. Well, so it's 3 5-gallon pails to a meter. Pick up 300 of those in a straight line. Not a bodybuilder in the world that could lift that. Okay, so let's get into some numbers here. 9.81 kilonewton meters cubed. We are 100 meters wide. We have an L now of 33.5, but we're squaring it. Be nice to put the meters in there, Michael. Squared, all divided by 2. And then we're going to go sine of 63.4 degrees, cosine of 63.4 degrees. And we're going to get a number that is in the ballpark of 221,700 kilonewtons, or 221.7 meganewtons, or the one that's much more preferred in the world of modern engineering is this, 10 to the third kilonewtons. Okay. Even at 21.7 times 10 to the third kilonewtons, you know a bunch of math in the past. That's a lot of weight. Okay, a lot of force.
Why don't you look at the number for it?
What's that?
I'm just wondering.
I don't know. I don't know. Geologists don't do that, so I didn't get that as an undergrad.
So, all right.
I don't like it.
Just to help out here, it's one of those topics. It's just crazy. So, geology's been around for a long time, but it's still in its infancy. Okay, engineering's been around longer, and we were forced to come up with unit notation based on a typewriter. Okay, now you can't do 10 to the negative 6 on a typewriter for two reasons. One, they don't have a caret sign to put in there that says -6 like the modern computer does. Okay, so they literally got the point was they started putting in this mega stuff, okay, or killa stuff. Now, you want to have some fun? Mega is, in this particular case, is the 10 to the 6 SI units.
I get the mega. It's that far right one.
Yeah, I know. Just bear with me. And then, but M also stands for 1,000 in Roman numerals. And England was under the rule of the Italians when the Romans invaded. Okay? Duh. Yeah. They left behind what was classified as the imperial system for the Roman emperor. Okay? Imperial Rome left behind their measurement systems using Roman numerals. So, we would have never used K in newtons. We wouldn't have used in newtons. We probably would have been stones. Thank God we don't have to go do that English system. Because there are people that know how many stones they weigh. It's like, cool. But, it used to get weighed, and how many stones you weighed was how much money you were worth, and they'd give you money or something if you're the king. Dumb. Okay? Why? Well, because stones were the easy way to do it. Now, here's a kicker. Find me 4 stones that are the exact same size and shape and volume and density. Mm-hmm. That would have been a riot back when we didn't know how to do that. Somebody did, because they had to have something consistent. But I bet they guarded those stones with, to the death. It's like someone stole a stone system, and you literally corrupted the whole economy of the king. So anyways, literally a lot of this stuff comes out of tradition. It's old tradition. It's a stupid tradition. I don't personally care. I'd prefer if you worked in the metric system for everything, because it's a lot more easier, makes more sense. But no, we're in the cubic foot systems. And then I go to Canada, and I expect the engineers over there to do things in the SI system. No, they do it in cubic feet per second for flow rate still. It's like, what the hell? And then I found out from somebody who I met from England, it's like, they still talk about road travel in miles. It's like, but you're metric. Why don't you do kilometers? Oh, we do it in miles. It's like, because all their stupid milestones are put in the dirt along the roadside. They know in miles. At least in France, everything goes into the metric system.
To be fair, they invented the metric system. So.
Yeah, well, it's important. All right, so anyways, cool. Now that we got our 2 weights, and let's go back up and review the free body diagram. So we know that one, and we know that one. Okay, that's supposed to be a check mark, not a V. Okay, how do we find FR? Yep. So FR is equal to the square root of FV squared plus W. Oh, this is a good way to do this W2, by the way. And I just did it in my notes here, and I didn't do it there. Put 2 little lines at the top. Yeah. So if you write a W like this, and you want it to be bold, put 2 little toppers on it.
Wait, is that the capital W?
That's a capital W.
Oh, okay. See, I might find lower W, like...
Yeah, I know, like
curvy.
This.
Yeah.
But trust me.
Yeah.
Yes, which
right.
is width up here someplace.
Yeah.
I did it. It's, where'd it go? Right there.
Yeah.
It's curly. But when you're trying to make things stand out and you don't have the ability to go put two tops on it. Okay? Then you know it's the W you want. Right? Literally in the textbooks, they get carried away and they actually just print it with bolder font and make it big, black, and bold. So it's not always easy to do in your homework. So anyways, plug the numbers in. So this is where it's nice not to have all the 10 to the 6 and stuff out there. (22) 1.7. And if I did my math right, our resultant should be this. And that's the answer. So really, on your comp paper, do 493.4 meganewtons, and then put your FR out here. Up here, you'd have W. Up further, you would have had FV. Okay. All along the outside edge of your comp paper. All right. So far, so good?
So the original question wanted the resultant force and the
Center of pressure.
center.
Yep. So, are you ready?
Well, I'm not anymore. I mean,
Okay.
Intimidating.
I thought I was ready. I guess not.
By God, you're going to have so much fun. All right. So, YR, that's a lousy Y, equals Z over 3, which equals 30 meters. Okay? This you know. Okay? But, here's how this is going to play out. And this is another equation from the book. So, actually, I'll give it to you over here. And the next time you teach this, you'll probably call me.
Ooh, you dropped something.
That didn't sound good, whatever it was.
Yeah, it was probably right. It was a calculator. It's probably all right. Yeah, it works.
Oh, because it's there. Because it's there.
And it's sub W.
Is that sub W or is that times?
Oh, that's sub W.
Oh, it's even worse. Wait, is the X part of the subscript as well, or is that?
The X is a subscript on the weight.
And then
So that's
W
a double
is-
subscript? Oh.
It's just a label. That's all it is. You know, there's no hard math with it. It's just, it's a label.
Wait,
But
so that doesn't relate to like if you have a slope and then a flat slope and then like that.
It does.
It does. Okay.
that's why I put it in here and why we're doing it the hard way. Because honestly, where's the center of pressure on this thing? 1/3 up the L of 33.4, right? We'd be screwed up if we didn't figure that out. Yeah. Don't you have to be in Potsdam?
No, not on Fridays.
Oh, cool. Sweet.
Potsdam doesn't work on Fridays.
The second free body diagram that you drew, where you put like the COP.
Yeah, this thing.
So that makes me think that we could do Pythagorean theorem of FB and the 10 meters there to get COP. Am I looking at it wrong?
Yeah, but don't go there yet. Because what we're dealing with is this mess over here, which you're going to have to get used to. All right. So, yes, honestly, to solve this particular problem, we don't have to worry about all that weight x over y's. But I want you to, what I learned over the years is it's really nice to systemize your calculation. Okay? If you don't systemize it, you're going to forget to do something. Don't be the engineer that went, oh, I'm just a shortcut. And you do a shortcut all the time, and you forget what the real way is. Then you're going to be on yourself. Okay? Yeah, Dom. Or are you just stretching?
Oh, no. Sorry. So in that example, when we get to it, we would have that first box there at the top. That'd be one weight. There'd be one weight related to that. And then that triangle there is going to have a second weight related to it.
Yep.
And then the full body of water is going to have a third weight. Or no?
No, they'll add together.
Oh.
Yeah. But anyways, so hang with me. This job. So where did all this mess come from in this? Okay.
The Romans.
Yeah, the Romans. Oh, sorry, I did that. We were. Oh, geez, I'm sorry. Oh, I got carried away. Up here, I'm just going to erase it so you can see it a little better. This is multiplied times xw.
Okay.
Yeah. Yeah. Sorry, I was having too much fun. Anyway, where's it come from? Moments. So the moment of the reaction of FR times its LR gives me the moment R. The moment vertical is based on the force vertical times its YR. Okay. Moment of weight is its weight times its moment in the x direction of weight. So far with me?
Yes.
And you guys are very fortunate. Somebody picked Dr. Regal up for lunch and explained to her what a moment is.
Did you know I was thinking that right
Because
now?
she is sitting here going, I want rocks in the worst way.
What the heck is a moment?
It's a torque in the physics world. Okay? Remember torsion?
Barely.
Yeah. They all get it. I know they do. The sad part is I just knocked off about 2 layers of dust from statics in strengths, haven't I? Yeah. All right. So literally, if you look at this equation, this part right here is the moment of V. This part right here is the moment of the weight. And I'm solving for LR, and I divide the whole thing by the resultant force. Okay? It's not like I did anything magical. I just put it in perspective of where that came from. Because no joke, even when you guys had the textbook doesn't explain this. Oh, and here's the equation you want to play with. Have a great day. It's like, I don't remember who it was a couple of years ago asked. It's like, oh, great question. That's moments. Yeah. Anyways, like I said, I'm the one that has fun around here. And you guys are just suffering through things.
I wrote moments and underlined it with an exclamation point.
So remember this.
I can play excited when I do this.
Sum of moments has to equal 0.
Yeah.
Eee. We're not going to go that far, but I just like to remind people of that.
So does that mean that we're going to have like a negative moment on one of these?
No, because we're not actually going to calculate the moment. We're going to use that whole sum of moments bit to figure out what that LR is. But remember, you write it up as sum of moments equal to, actually I could do it here. Sum of moments equal to MR plus MV plus MW. And we're solving for MR, but we're going to solve deeper into getting the LR. So,
But
fair
I
enough.
mean, for those to add up to 0, one of them would have to be negative.
Oh, yeah. No, sorry. Yeah, they got to balance out. Otherwise, it keeps rotating in space, and we're pretty sure that the planet stays put, and the dam doesn't keep rotating across the planet and so on. What are we doing? Oh, crap. We're out of time.
Yes.
Ah! Okay, Monday.
Shame.
Actually, the sad part is it's really just about 66 numbers. Can you guys in a rush? Can I give you 5 minutes?
Well, we better hope so. Already been here early. But,
Yeah, so you don't have to
early, Salari. Yeah, actually.
So there's something I don't want to know about. All right, so anyways, 1 over 493.4 meganewtons times 440.8 meganewtons times 10 meters, need your parentheses in the right places, plus 221.7 meganewtons times 5 meters. Where did the 5 meters come from? Oh, I know where the 5 meters come from. I didn't do that in the diagram, which I would have done. So think of triangle like this. We're 30 meters here. We were 5 meters there. Okay? And we're actually going to figure out where XW is from there. So it's where's the other 1/3 of the centroid kind of stuff. Remember that stuff? Yeah. Okay, so XW, sorry, this is 15. XW equals 15 divided by 3 equals 5 meters. Okay, so that's our location for that. So that's where the 5 came from in this equation here. Okay, and when we get all done, we solve this. We're 11.1 meters. That's the other answer. So your COP will be over there. Cool? Now, is 11.1 in perspective to the 10 if it was vertical? If we didn't have an inclined surface and it was just vertical, and we said it was 10 on the vertical, is 11.1 a reasonably right number when I lean it back?
Right.
Yeah.
It's insane.
So that's the other thing. Validate your answers to yourself. Okay? All right.
split verify.
So what is it actually that you
What's that?
It's 11.1?
The center of pressure. So back up here, right here to there, LR is 11.11.
So this is, we're finding COP or L?
Yeah, for the COP. It's LR. Center of pressure.
LR is COP.
Yeah.
Okay.
Cool? It's fun, isn't it?
Why did you divide 15 by 3?
Because I am in a triangle over here looking for a centroid in the X direction. So this is the beauty of I really like fluids, because when you did this for statics, all we ever found was where's the centroid in the y direction. We didn't mess around with the other dimension at all. Okay?
Where'd the 15 come from again?
It's the trig of getting the
that's just
opposite.
the length at the top of the triangle.
So it's 30.
So the top's not 5.
No, top of it.
15.
Oh, okay.
It's a 1-to-2 ratio.
Okay. The
So
adjacent is.
It's
Oh,
it's 2 up,
okay.
1 over
Okay.
the right, which would be get half
Okay.
of 30 is 15.
Okay.
Or you could do the trig. And by the way, is it her birthday and is she dressed like Britney Spears?
Not Britney Spears.
Oh, sorry.
Taylor Swift.
Taylor Swift.
Thank you.
Yeah, that's right.